Welcome to Microlecture 4, where we will talk about hybridization. The theory of orbital hybridization is that atomic orbitals mix or hybridize, and there's plenty of evidence of this. Atomic orbital hybridization is consistent with VSEPR theory. The idea is that valence orbitals, S and P in particular, will mix to form hybrid orbitals. These hybrid orbitals better describe the molecule's characteristics, like polarity, and bond length, and bond strength. Take the oxygen in water, for example. If you were to fill out an electron configuration for the oxygen, you would start with two s orbitals in the valence shell and move the electrons then into the two p orbitals once the 2s is filled. With 6 electrons in its valence, this oxygen has 2 covalent bonds of equal length and strength, and the only way to describe this is to come up with a model that allows for all 4 regions about this oxygen to be pretty much the same. Indeed, the 1 2s orbital and the 3 2p orbitals will mix to form 4 sp3 hybrid orbitals. So take a quick moment here and draw out the electron configuration for carbon. So if we were to come up with the electron configuration for the carbon and methane, we would have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and then we'd have the 2p orbital. There's 3 of them. We know that carbon has a total of 4 valence electrons. So between the 2s and the 2p, we have 4 valence electrons. We've already got 2 in the 2s orbital, and so we fill in 3, 4. But there's no way that this could explain how methane has 4 equal length and equal strength bonds. So what happens is that these valence electrons, the ones in the second shell, will mix to form 1, 2, 3, 4 sp3 hybrid orbitals. And according to the rules of electron filling, they're all same energy, so we would go ahead and fill in 1 electron across the board. And this is how and why carbon forms 4 strong covalent bonds. So a quick tip here, to determine the number of hybrid orbitals that you have around an atom, count up the sigma bonds and the lone pairs. This carbon has no lone pairs, but if you count up the bonds, there's 4 of them, and so we do expect to have 4 hybrid orbitals. Okay, let's go ahead and do the same thing now, but for C2H4, ethylene, otherwise known as ethane. This is a molecule with a carbon-carbon double bond, and then we've got 4 hydrogen atoms around the periphery. So for that carbon, either one of them, they're the same, we want to know the hybridization and understand why it is what it is. It turns out it is sp2 hybridized. If we were to write out the valence electrons in an electron configuration diagram, again, we would have 2 electrons in the 2s, and we would have 2 electrons in the 2p. And so what happens here when we have double bond formation is these orbitals will mix to give 3 hybrid orbitals, and then there's 1 p orbital that's left over. This one that doesn't have any electrons in it is sort of left over here. Okay, and so the only ones that are really hybridizing are these 3 right here. And so we get 3 sp2 hybrid orbital and one leftover p orbital. And so these electrons will fill this way, and with one electron in each sp2 hybrid orbital, that is how the carbon forms 3 sigma bonds, and with the electron in the p orbital, that is how the carbons will pi bond to one another. So let's draw a picture of what carbon-carbon double bond formation looks like. If we consider that an sp2 hybrid orbital, it looks a little bit like a p orbital. If you know what a p orbital looks like, kind of like an infinity symbol. And an sp2 hybrid orbital looks like that, except it's a little bit lopsided and it has one longer side and one shorter side. So the shorter side, that would be the carbon's core. And so this carbon would have 3 sp2 hybrid orbitals. One of them would be overlapping with a hydrogen's s orbital. Another one of them here would be overlapping with the other hydrogen's s orbital. And the third one, it's oriented this way so that it can overlap with the other carbon atom's sp2 hybrid orbital. Let me go ahead and complete my drawing then with the 2 more sp2 hybrid orbitals here, and the hydrogen atoms that each have an s orbital overlapping. Okay, and so what I've just shown is how all the sigma bonds form. Sigma bonds form through direct orbital overlap. So there's a sigma bond, there's a sigma bond, there's a sigma bond between the 2 carbons, and then 2 more. So for a total of 5 sigma bonds. What's left is the pi bond, and if you recall, there was a leftover p orbital, and that p orbital is right here, and there's another one on the other carbon right there. In order for p orbitals to form a pi bond, they must be coplanar, that is, pointing in the same plane, in the same direction. And this is sideways electron overlap, not direct electron overlap. So the electron density is spanning a larger range than direct orbital overlap of sigma bonds. But there you have it. That is how the pi bond forms in ethane or ethylene. The same thing is true for pi bond formation in ethine. So ethine is a carbon-carbon triple bond containing molecule. And so let me go ahead and share with you this idea while we're at it. The carbons here are sp hybrid. And an sp hybrid orbital looks a lot like an sp2 hybrid orbital, so we'll just draw it the same way. Each carbon has 2 sp hybrid orbitals, just like so. And the carbon-carbon bond, at least the sigma portion of it, is forming through direct orbital overlap of 2 sp hybrid orbitals. We do have the s orbitals of the hydrogens sitting here, and so again, that direct orbital overlap allows for these sigma bonds. There's 3 of them. 2 of them are carbon-hydrogen, and the central one is a carbon-carbon single bond. And so then there are actually a couple of leftover p orbitals. And remember, to form a pi bond, the p orbital has to be pointed in the same direction. And so we've got one pi bond formed right there, and then it's hard to see because perpendicular to that set of p orbitals that we've already got drawn. So if we could think of going in and out of the plane of the screen or of the paper that you're drawing on, you've got another p orbital, and overlap of those two p orbitals is what's going to give you the other pi bond. Okay, so we've got pi bond there and another pi bond there. So two pi bonds. So a triple bond is made up of a sigma bond and then two pi bonds. Okay, so go ahead and pause the video here and draw acetic acid. You're probably getting very good at drawing the Lewis structure of acetic acid, and then identify the hybridization of each of the atoms in acetic acid. Okay, so I've gone ahead and drawn the structure for acetic acid, and we're going to go ahead and identify the hybridization of the carbons and the oxygens. The hydrogens are not hybridized. They have just a 1s orbital that does not hybridize. So the carbon with 4 regions of electron density, this first carbon, 4 regions of electron density is caused by having 4 sp3 hybrid orbitals. So that's sp3 hybridized. The carbon with 3 regions of electron density has 3 hybrid orbitals around it, and those are sp2 hybrid orbitals. Same with the oxygen on the top. The oxygen has 3 regions of electron density, 2 lone pairs, and 1 bonding region. And so that is caused by the oxygen being surrounded by 3 sp2 hybrid orbitals. Each of those lone pairs then is located within an sp2 hybrid orbital. And then the last oxygen has 4 regions of electron density. So that is created by having 4 sp3 hybrid orbitals. And so those lone pairs are located in sp3 hybrid orbitals. The question asks to draw the p orbitals that make up the pi bond. And so those p orbitals would be, pick an interesting color here. So there's, for each of these sp2 hybrid atoms, there is a p orbital that is left over after the 3 orbitals combine to make sp2 hybrid orbitals. So that pi bond is formed through parallel overlap of electron density between these 2 p orbitals. In this second example, let's do the same thing. Identify the hybridization of each atom and draw in any p orbitals for acetonitrile this time. Acetonitrile consists of a carbon-nitrogen triple bond, and then a CH3 group on the other side. So the hybridized atoms here are this carbon, and this nitrogen. So carbon with 4 regions of electron density is sp3 hybridized. Carbon with 2 regions of electron density is sp hybridized. And a nitrogen with 2 regions of electron density is sp hybridized. And we want to kind of think about the location of p orbitals that would make up pi bonds. And so we've got 2 parallel p orbitals here, causing 1 pi bond formation. And then if we can think about perpendicular to that, so in and out of the plane of the board or screen or paper, there's these other two parallel p orbitals, and that is causing the formation of the other pi bond.